Welcome to The Explainer. Okay, today we're taking on something that honestly sounds kind of impossible. We are going to measure something completely invisible that moves at literal lightning speed. Yep, we're talking about capturing and measuring the exact speed of sound right on your own desktop. We're going to do this using an HCSR04 ultrasonic transducer and an Arduino Uno microcontroller. It sounds like straight up magic, but I promise you it's just pure applied science.
Okay, let's dive into this roadmap. We'll start with the physics of echoes, wire up our ultrasonic sensor, and then code the sound wave itself. After that, we'll read the results and, finally, dig into why the speed of sound actually changes.
So just think about this for a second. How exactly do you measure the invisible? Capturing an acoustic wave's speed sounds like a massive challenge, right? Like something that requires a multi-million-dollar acoustic physics laboratory. But the brilliant reality here is that we can solve this problem using an incredibly clever, totally affordable piece of electronics, the HCSR04 transducer. It's this tiny little device that pulls off an absolutely massive mathematical feat.
All right, Section 1, the physics of echoes, theoretical physics and kinematic principles.
Before we even think about plugging in any wires, we need to be methodical and really understand the underlying mechanics. Our sensor is equipped with an integrated piezoelectric transmitter. Now, its entire job in life is to shoot out a series of high-frequency pressure waves into the air, specifically 40 kilohertz acoustic pulses, which are way beyond human hearing. This whole system relies on a concept called time of flight. It's basically a method to figure out position by measuring the exact time it takes an acoustic pulse to hit a boundary and bounce right back. Imagine throwing a tennis ball, imagine throwing a tennis ball hard against a brick wall and catching it. If you knew exactly how long that ball was in the air, you could easily figure out how fast it was traveling. Our sensor works exactly the same way. It just waits for that sound wave to strike a flat boundary and return as a mechanical echo to the receiver microphone.
Here's the absolutely crucial part to remember. This acoustic pulse is making a round trip. The sound wave has to travel the physical separation distance twice. First, it travels from the transducer to your reflecting wall, and then it bounces backward to the receiving matrix. Because of that round trip, the net mechanical displacement of the sound wave is exactly twice our static reference distance. We simply represent this as 2 times d.
Which brings us to this really beautiful classical kinematic equation. V equals 2 times d divided by t. Let's unpack that real quick. V is the calculated velocity of our sound wave traveling through the air in meters per second. D is the pre-measured physical distance to our wall in meters, which remember we multiply by 2 for that round trip. And t is our time of flight in seconds. The microprocessor's internal timer is going to precisely record that t value for us. Section 2. Wiring the ultrasonic sensor. Hardware wiring and schematic interconnection.
Now, what's really interesting about this setup is how we take all that abstract math and connect it to a physical, tangible build right on the desk. Let's methodically guide through the pinout mapping to ground our theory in basic electrical engineering. So the HCSR04 sensor has 4 pins. First up, VCC. That's your power supply, which links directly to the Arduino's 5-volt power rail. Next is trig, or the pulse input. We map this one over to digital pin 9. This is the pin that actually tells the sensor to fire the sound wave. Then we've got echo, the pulse output, wired up to digital pin 10, which listens for that return wave. And finally, GND goes right to your common ground rail to complete the circuit. It's just a wonderfully simple schematic.
But hold on, before we power the whole shebang on, we really must respect some critical setup constraints. Sloppy environments will absolutely ruin precision measurements, for sure. First, you've got to mount the ultrasonic assembly securely to a stable platform, because any baseline vibrations will totally skew your timing. Second, you need to place a completely flat, non-porous obstacle, like a hardcover book or a solid wood block, at an exact measured spacing distance of 1.00 meter or 100.0 centimeters. Finally, you absolutely must ensure a clear line of sight. Any random side tables, loose wires, or coffee mugs sitting around will cause stray edge reflections, and that completely confuses the acoustic projection. Moving right along, Section 3. Coding the sound wave. High-precision firmware implementation via a C++ sketch. This is where we shift gears from hardware over to computer science. The C++ sketch we write for the Arduino is the brain of the operation here. It establishes a hardware serial stream at a standard 9600 baud rate. Think of our code as having a highly active micronarrative of listening, broadcasting, and computing. Step 1. The loop maintains a clean baseline condition by holding the trigger line low for 2 microseconds. Step 2. It broadcasts the sonic signal by cycling that trigger pin to high for exactly 10 microseconds.
Step 3. It actively monitors the echo flight time duration, capturing the precise exact moment that sound returns. Step 4. It translates those raw microsecond values into seconds and calculates the velocity. Oh, and crucially, it rests the program for 1.5 seconds at the end of every single loop, just to prevent any weird wave overlapping anomalies.
And you know, this perfectly illustrates the need for fail-safes in data collection. Our C++ code is intentionally designed to actively trap anomalies. If the evaluated flight duration comes back as 0, meaning the signal dropped or just timed out entirely, the console spits out this exact warning. Hardware error, echo return pulse undetected, verify target path. This is great because it ensures that a missing echo doesn't accidentally register as a 0-second flight time and completely break our mathematical model.
So when the code does receive a valid microsecond pulse, it jumps right into the kinematic math conversions. It translates the flight time from its raw microsecond format into standard seconds simply by dividing by 1,000,000. Then it scales the path length. It takes our 100-centimeter calibration distance, converts it to meters, and multiplies it by 2 for the net loop path length, giving us 2.0 total meters. Doing all this provides standard metric velocity inputs for our final speed of sound calculation.
Section 4. Reading the results. The expected serial terminal text stream output. Let's move ahead and see how this all builds into tangible, real-world data inside the Arduino desktop tool suite environment. When you open up that serial monitor window, you'll see a continuous text log feed. For our 100.0 centimeter setup, an echo round trip of 5,831 microseconds outputs a computed wave speed of exactly 343.0 meters per second. The very next loop might show 5,848 microseconds, yielding 342.0 meters per second. The system is smartly truncating the formatting down to a single decimal place, giving you a beautiful, live look at a completely successful measurement loop. Look closely at that number right there, roughly 343 meters per second. I really want to spotlight this punchy baseline metric because it is the definitive, expected speed of sound in nominal room conditions. Watching your own custom-built hardware output this exact fundamental constant of nature, proving it right there on your desk, is just an incredibly rewarding learning experience. Finally, Section 5, Why Sound Speed Changes. Let's do a quick acoustic fluctuations analysis. You've probably noticed that in real-world testing, that wave speed isn't perfectly static, it naturally fluctuates a little bit. Well, the most significant factor for this is called the thermal dependency vector. Basically, sound waves scale heavily with the surrounding ambient temperature. In a standard dry atmospheric environment, the speed curve follows this formal expression. V is approximately 331.3 plus 0.606 times T, where T represents the temperature in Celsius. So the actual physical medium the wave travels through literally changes depending on how warm it is. To put that into perspective, let's contrast a normal room with a hot chamber. At a nominal room temperature of 20 degrees Celsius, sound tracks exactly to that 343 meters per second mark. But if we place our Arduino setup in a hotter testing chamber, the reduced air density actually results in accelerated sensor values. Literally, heating up the laboratory speeds up the acoustic velocity of the wave. Pretty wild, right? And actually, setting thermodynamics aside for a second, we also have to account for hardware precision jitter. The standard HCSR04 modules carry a normal operating accuracy tolerance window of about 3 millimeters. This mechanically shifts the pulse capture threshold slightly by just a few microseconds, frame over frame. So I want to reassure you, those minor speed calculation fluctuations popping up in your terminal are totally normal, and they just represent the physical manufacturing limits of the module itself. Which kind of leaves us with this final, really provocative thought. If simply having a hotter room speeds up sound, how do high-end, precision ultrasonic instruments, like those used on deep-sea submarines or in blazing desert surveys, how do they account for extreme environments? It really makes you marvel at the immense complexities and physical variables acting on simple electronics every single day. I hope this explainer gave you a fantastic foundation in acoustic velocity, and that you are leaving here feeling completely empowered to build and code this setup for yourself. Keep learning, keep experimenting, and hey, thanks so much for joining me.